This is Rosen, Discrete Mathematics and its Applications, section 10.7 on planar graphs. And this video will cover down to Euler's formula. The proof of Euler's formula will be a separate video. All right, so here we have a utilities model, 3 different utilities going to 3 different houses. And is it possible that I could connect these utilities so that I didn't have all these crossings? Maybe I could take this electric that way and then this electric that way. Is there a way to do that? The model, as you can perhaps tell, is really K33. It's a bipartite graph with 3 vertices in each bipartite set. It turns out that the task is impossible to do, and we'll show you how we know that in a little bit. But it's also going to be useful to decide when we can draw graphs without edge crossings. All right, so a graph is called planar if it can be drawn without any edge crossings. And such a drawing is called a planar representation. So our K4 and Q3 planar, here's K4. Can I draw that without the edge crossing? Sure, I can take that middle, one of those interior edges and move it to the outside like that to get K4 with no crossings. How about Q3? Here's Q3. I see 2 crossings. Is there a way to represent that with no crossings? Well, if you imagine yourself looking down into a box from an open lid, you might see that, and there's a representation of Q3 with no edge crossings. Okay, in order to describe planar graphs, we want the concept of a region. And so that's a contiguous area enclosed by a set of edges in a planar representation, and also the area outside of a graph is considered a region. All right, so let's tackle K33 again. We want to know, is it planar? Well, let's start with a planar portion of it and see if we can build up to a planar version of K33. We're going to take V1, V2, V4, and V5. We're going to flip V2 and V5 and get that subgraph. That's a planar representation. I've got 2 regions, R1, R2, and R1. Now I want to add some vertices. I'll add V3 first. And V3, if I connect them to V4 and V5, like I do in my K33, it will divide the region that it's placed in into 2 different regions. I could have put V3 in region 1, but it would have divided region 1 into 2 regions as well. All right, so now I've got 5 of the 6 vertices. What happens if I try to put V6 in there? Well, it's going to have to go into region 1, region 2, 1, or region 2, 2. But as soon as I try to do that, if I try to put that into any of those regions, I'm going to require an edge crossing. Because if I put it in region 1, it's got to cross an edge to get to vertex 3. If I put it in region 2, 2, it's got to cross an edge to get to vertex 1. If I put it in region 2, 1, it's got to cross an edge to connect to vertex V2. All right, so that is a proof that K33 is non-planar, and our introduction to regions. What are some of the applications? Well, we kind of little feel for that with that first slide on utilities, and we might want to avoid layered layered conduits or something like that, or pipes. If you have edge crossings in electronic circuits, that could require insulation, may have some reliability concerns if you want to avoid edge crossings in a circuit. What about roads? Well, if an edge is a road and they cross, you're going to have an intersection that has to be managed, or more expensively, a bridge that has to be built. So that'd be some of the reasons you want to avoid edge crossings. Okay, Euler, still active in the realm of graph theory, has came up with a very important formula. Let's introduce that. If I've got G as a connected planar simple graph, sometimes I abbreviate that CPS, connected planar simple graph, and I've counted up the edges, and there are E of them, counted up the vertices, there are R of them, and I've counted up those regions, those areas that are bounded by the edges, contiguous regions bounded by edges, and it turns out that if I have a planar representation of G, then the number of regions is equal to the number of edges minus the number of vertices plus 2. Now, we'll do the proof of that in a separate video. How can we apply it? Well, there'll be a number of ways. Just quickly, though, if I have a CPS graph with 20 vertices, each of degree 3, how many regions does it split the plane into? Well, R is equal to E minus V plus 2. 30 edges minus 20 vertices plus 2 gives us 12 regions. Well, where did I get 30 edges from? Well, 20 times 3 equals 60, and the sum of the degrees of the vertices is equal to, equals 60. That equals 2E, so E equals 30 from the handshaking theorem. All right, and that is your introduction to planar graphs, and we'll tackle some theorems related to those in later videos.